recording. Okay. You know, back in the day when we were doing approximation of derivatives, we would do like f of b minus f of a over b minus a, right? And that was like the approximation of slope between 2 points, right? And the closer and closer together we got, the more exact it is. Well, the opposite of a derivative is called an integral. Now let's think about why this happens. Okay, let's say I have velocity graphed. So let's say I have the graph of velocity. And instead, so this is f prime. V of t or f prime, right? So graph of velocity is, and f prime is the same thing as saying change in y over change in x, right? Yes? Yes? Okay, so we have that graph. This will be in time or x, whatever our input is, right? Okay, now we've got...
Do I have to take notes on this?
No. Okay, so let's say we've got this velocity graph right here, okay? Now, if I find the area under this curve right here, if I find all of this area down here, then I will be multiplying the height or the velocity, right? Velocity times my time, right? That's how I find area. Base times height, right? Times time. Well, what's velocity? Give me a set of units for a potential velocity. Meters per second. If I take meters per second and then time is in seconds and I multiply by seconds, what happens? It crosses out and I get back to meters, right? So when you find the area under the curve, it kind of undoes a derivative because here you have a rate of change, and when you integrate it, you go backwards to just meters. Yeah? All right. So that's the whole point of integrals, is to do it's like the inverse operation to derivatives. So it's kind of like addition to subtraction, multiplication goes with division, derivatives goes with integration. But before integration, just like before we found tangent lines and we did limits, the only way to approximate the area under the curve was to make little rectangles or squares. Do you remember back in like elementary school where they had you like count up all the squares to add up the area underneath like a certain section? Do you remember that? No? Yeah, you you count up all the squares and you're like, oh yeah, that's 27. Yeah. And these two sections kind of look like they balance each other out, so that makes one full square, right? So that's basically what you were doing back then. You were doing simple integration while you were doing Riemann sums. Okay? So we could only approximate the area under the curve by making, there's 4 different ways that we do Riemann sums, but we make rectangles for 3 of them, and then for the 4th one, we make a trapezoid. Okay? All right. So we just make little rectangles, and then we add up all of the rectangles. That's our approximation. Okay? So let's say we start with this function, f of x equals x minus 2 squared plus 8. So that is a graph shifted left 2, up 8. I made it nice for us. And then it's down 1 over 1. And then the next one is 4, 4. And then the next point's down here. Maybe I shouldn't have. So here's our parabola. Make a nice one. Make it nicer than mine. I messed up. I got scared at the end. Okay. So it says we want to find the area bounded by the function on the x-axis with the interval 1 to 5. So we're going to start at 1, and we want to find the area all the way up to 5. This one's off, but whatever, we can still do it. Okay, so first we need to know the size of our rectangles, because if we want 4 subintervals, then I'm going to go from 1 to 5 with 4 in between. How many rectangles? 4 rectangles, a width of 4, so each one is 1 apart. But if you didn't know that, or if you couldn't calculate it, because their numbers aren't easy, you would do 5 minus 1 divided by the width of the bounds of your area divided by the number of rectangles that you want. 5 minus 1 is 4. 4 over 4 is 1. So each rectangle will be a delta x of 1, a width of 1. Okay.
Can we just approximate it? Let's see. 1 to 2 is 1.
Yeah, but sometimes they're not as nice. So I'm just showing you how to do it if it's not an easy one. Okay, so you want to make a table from 1 to 5, but choose. Now we go a width of 1 every interval. So a width of 1, a width of 1, a width of 1, and then a width of 1. So from 1, this would be 2, 2 at plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5. Okay? All right. Now we figure out our y values by plugging 1 into the original, but I also have it graphed. 1 has a y value of 7, 2 has a y value of 8, 3 has a y value of 7, 4 has a y value of 4, and 5 has a y value of negative 1. Okay? All right, our chart is done. If you ever have a chart, you want to, I always make space for, if I want 4 subintervals, I make squares for 5, and then put 1 in the front, 5 in the back, and then divide the middle evenly. So the number of lines of separation you should have is 4 here, because you want 4 subintervals. Okay, let's do our Riemanns. Let's add them up. So we're going to do a left sum right now. So left sum means that we're going to start at 1, go up to where I intersect with the graph, and then we're going to draw a rectangle straight over until I hit my next interval that I need to do. So my rectangle goes straight over until I hit 2, and that's my first rectangle. Okay. And then at 2, I go up to 8, draw a rectangle over to my next intersection, which is 3, and then go straight down at 3. At 3, go up to 7 again, over, and then down. And then at 4, go up to where you intersect with the curve at 4, over, and down. So my total area would be that these 4 rectangles right here will be my approximation. So that section, that one, and that one. These bottoms aren't here. I don't know. My highlighting skills aren't the best. Okay. All right. So my left sum approximation would be a width of 1 every time, right? So it's 1 every time. So this one, and then my height of this rectangle will be 7. So this is 1 times 7. This would be 1 times a height of 8. This is 1 times 7. And this is 1 times 4, right? Okay. So there's 2 ways to write it. For less sum, you can do 1 times 7 plus 8 plus 7 plus 4, because the width of your rectangle doesn't change. Or if you want to write it all out, you can do like 1 times 7 plus 1 times 8 plus 1 times 7 plus 1 times 4. But that equals 26. Okay. If you're doing this on your own, you can make the rectangles equal widths. But sometimes they don't give you rectangles of equal widths when you're doing a table, so you cannot do it this way. You've got to do it this way. If they don't give you, like if your intervals for the tables are split not equally, you've got to do it in separate parentheses. Okay. All right, let's copy the graph again for the second one. 4, 7, 8, 7, 4, -1. Okay. And then let's do a right Riemann sum. So the right Riemann sum means that I'm going to go in between 1 and 2 is my interval in between 1 and 2, but instead of going up to 7, here, I'm going up to the right side in between that interval. So I'm going up to 8. So 2, we go up to 8. But then we draw a rectangle to the right and then down. In between 2 and 3, I choose the one on the right-hand side, which is 3, so we go up to 3 and draw a rectangle over and then down. In between 3 and 4, we choose 4, 4 as my point, draw a rectangle up and then over, and then at 5, my rectangle is down here at -1, so we're down here. And so my rectangle's down here. So the area, you can have negative area when it comes to integration. So, all right, so my approximation will be here. This section, this section, this section, and this section. Or 1 times 8, 1 times 7, 1 times 4, and 1 times -1. Okay, so right sum, when you look at it from here, we could, or when you look at, let's look at it from the table view, you would do an interval of 1 times, so you would look in between 1 and 2, and you would choose the right one of those two, so you would choose 8. So you would do 1 times 8 plus, and then you would look at this interval, and that's from 2 to 3, and then we choose the right, the one on the right, so the width is 1 times 7. My width is still 1 from 3 to 4, but I choose 4 for my right one. And then my width from 4 to 5 is 1, but I choose -1. Same thing as like the visual up here. Since the interval is the same, you could leave the 1 out. And just multiply all of the heights. And then that would equal 18. Okay. Questions? So that's the left sum and the right sum. Shall we do midpoint? Now some guy was like, oh, well these are leaving out all this space. What's the better idea? The better idea is to go in between them. So if we drew our graph again, 4, 7, 8, 7, 4, -1. Okay. So some guy decided, I guess Riemann, he was like, oh, well, there's a better way. The better way is to go halfway in between 1 and 2 and go up to your y value here, right here, and then draw your rectangle out from there. So like halfway out this way and halfway out that way. But your width of your rectangle is still the same. It's still 1. But instead of using the left or the right, we go in the middle of the two. And then you'll get a little bit of this area, and you'll take away a little bit of this area, and it'll be more exact. Sometimes it is, sometimes it's not.
Are these just different ways to approximate?
Yeah, because they'll ask you, like, do a left sum, or do a midpoint sum, or do a
What
trapezoid.
is the best?
It depends on the graph. Yeah. Okay, we're going to go halfway in between 2 and 3, which is right here, and we draw a rectangle out and then down. And then halfway in between 3 and 4, you go up to this point, right here, and draw a rectangle out and down. And then halfway in between 4 and 5. It's right here. Okay. So your area for that one includes a little bit over and a little bit under. Okay. What do you think? Okay. And then the midpoint sum, ooh, this one's more annoying because I can't go back to my table and I can't use 1 and 2. I gotta go with 1.5. So I need these numbers in between. I need 1.5, 2.5, 3.5, and 4.5. So we've got to do a table x, f of x. And my table would be 1.5, 2.5, 3.5, and 4.5. So at 1.5, it says if you plug it in, you get 7.75, and then you get 7.75 for 2.5. For 3.5, you get 5.75, and for 4, you get 1.75. So the width of your interval is still 1. So you still do 1 times 7.75 plus 1 times 7.75 plus 1 times 5.75 plus 1 times 1.75. I don't know what that answer is. Thank you. Okay. All right. Sounds good? No. We're just drawing rectangles in here. What do you need a break for? Trapezoid. Okay, so trapezoid, let's draw our parabola first. And some guy was like, oh, I know a better idea. Let's do trapezoids to make it more accurate. And then, so the guy's, I don't know who this guy is, imaginary guy, said, okay, let's go from 1 to 2. But instead of drawing like a straight line out, let's just make a trapezoid and connect to the 2 like that. Yeah. It's the same thing as something. No. And then, no, bars are the same width for midpoint. But, oh, you might have to make fatter bars because if you're given a table, you gotta go from here to here and then you pick the halfway in between number, that's why. But if you have a function, you can find the middle. Okay, these two connect, but you are right, it is the same as something else. And then 4 to 5 is, this is a struggle, whatever. I think this is, so we'll have, I don't know what's going on here. Who knows? Just draw, I don't really know what's happening. This one?
Yeah. For this.
I don't know, midpoint looks kind of like pretty good too.
But don't you have like other stuff like going outside of it?
Yeah, but this one you're always taking like a little bit less. And this one you will have more here, but it might be compensated by what's missing here. Who knows?
Is there a way to find out?
Yes, there is. We'll do that later. Okay, so midpoint, here's what you do. Do you guys remember the area of a trapezoid?
Yeah.
No?
It's like base 1 plus base 2.
Yeah. So base 1 plus base 2 times the height, right? But we're going to turn it on its side and we're going to go like h1 plus h2 times the base. We're just going to do it a little bit because our trapezoids are vertical and we've got two different heights, not the base. So instead of base 1 plus base 2 times height, we're going to do height 1 plus height 2 times the base. But it's not just that, it's 1/2. So area of a trapezoid is 1/2 times h1 plus h2 divided by b. Okay. Or I think it's the average of the heights. So height 1 plus height 2 divided by 2 times the base. Whichever way you want to do that. Okay, so this one is 1/2 times 7 plus 8 times 1 plus 1/2 times 8 plus 7 times 1 plus 1/2 times 7 plus 4 times 1 plus 1/2 times 4 minus 1 times 1. Okay. Just wants to learn. Okay. Are you with me? Yeah? Okay. Kind of. Another way to write it is the 1/2 is on each one of them. So you could put the 1/2 on the outside for the trapezoid. The 1 is also, the delta x is also the same for all of them, so you could put the 1 on the outside. And then take a look at all of the rest of the numbers. What you have is, and this is only if you have equal intervals. If you don't have equal intervals, do each trapezoid separately. But if you have equal intervals, you have, this is what happens. You have 1, 7 from this point right here. You have 2 8s, so you double the 8s. You double the 2 7s. You double the 2 4s. And then you take -1 is the last one. So that's also trapezoid rule, where you take the first number and the last number in your chart, and all of the middles are doubled because all of the middle numbers are used twice. This number is used by this trapezoid and this trapezoid. This is used by this trapezoid and this trapezoid. This one's used by this one and this one. But the last one and the first one are only used once. So that's another way to write it. And then Chris was asking, isn't trapezoid like the same as midpoint? And it's not. However, I think this is what you're thinking. Trapezoid is the same as if you average the left and the right. Because think about it, if I took this one and this one, I added them all together and divided by 2, you would have this same formula down here. Sarah?
If the base is the same, can you still take out, or if the base is different, can you still take out the 1/2?
No. Oh, you can take out the 1/2, but you can't take out the 1. Yeah. If the base is the same, pull out the 1/2, but the 1's got to go to each term, or the interval's got to go to each one. Okay. So after lunch, we'll practice with a problem on the next page, and then we're going to do some summation notation.